In this lecture, we are going to discuss about a dynamical system which are known as uniform oscillators. Okay, so the dynamical system for this uniform oscillators are represented in the following manner. Theta dot is equal to omega, okay, just constant, and this is a system which can be represented as a flow on the circle. Okay, now this is a simple equation, so I could directly solve it, and if I solve it, I'll get theta of t, which is equal to omega t plus theta naught, where theta naught is the initial value of theta. Okay, so that's this equation, and if you see, it's an oscillatory function because after some time it will come back to its same position because it's a flow on the circle. In such a periodic function, a quantity which I will be interested is the time period. Okay, so which means after some time, let's call that time as t. Okay, after some time I will get the same theta value, which means t plus capital T, which is equal to theta of t. Okay, and that is valid for any t. Okay, then what is this capital T? That's what the time period is. Okay, so for this equation, what is the time period? Let's use this condition. So theta of t plus capital T, which is equal to omega of t plus capital T, okay, into plus theta naught, which is equal to omega of t plus and this is actually, this should be equal to plus 2 pi. Okay, so that's what this means. Okay, only the dynamic is periodic, but we'll have this 2 pi, and then we represent 2 pi with the same theta plus 2 pi as same as theta of t. Okay, omega of t plus omega capital T plus theta naught, which is equal to theta of t plus 2 pi, which is this one. Okay, so from this what I could say is omega capital T, which is equal to 2 pi, so which gives me capital T is equal to 2 pi by omega. Okay, so if I see a system like this, which is a flow on the circle, then the time period is very simple, which is just 2 pi divided by that constant. Okay, so that's the time period. Okay, so now we'll see an example where we could observe this uniform oscillatory behavior. So let's say there are two people, P1 and P2. Okay, and they are running on a circle, okay, a circular ground. Let's say okay, yeah, and then let's say the time taken for P1 to complete one round of the circle is T1, okay, and for him it is T2. Now the question is, say they initially start from some point, let's call that point is 0, okay, and yeah, one more thing is T2 is actually greater than T1, which means this guy is taking very long time to complete this circle compared to this guy, so he is actually slow compared to this guy, okay, fine. Now the question is, so since P1 is faster, so what he could do is, if he continue with that same speed, he could go faster. This P1, the person 1 could go faster, and once again he could meet this person 2 again, okay. The question is, what time it will take to make to have P1 meet P2 once again, okay. So that T, what is that T? Okay, so that's the question. Now let's see, so they are running in a same speed, so in that case, if this is a time period for person 1, so what is his angular speed in that case? So let's denote his position in the ground is theta 1, okay. So then theta 1 dot is equal to 2 pi by T1, sorry, yeah, 2 pi by T1, which is the omega 1, right, and then for theta 2 dot, that's actually 2 pi by T2, which is omega 2. Okay, so now what we have to do is, we have to solve this one and we have to solve this one, and then somehow we need to identify when the difference will once again go to 0, right. But if you see, it's actually sort of 2D system, right. So so two state variables, one is theta 1 and another one is theta 2. But for the question, okay, do I really need two state variables? Actually I don't need. All I need to know is the difference between theta 1 and theta 2, okay. So what I'm going to do is, I'm going to consider, instead of these two state variables, I'm going to consider only one state variable, which is just the difference, because that's what my interest is. So I'm going to introduce a variable phi, which is equal to theta 1 minus theta 2, okay. So if this is the case, then phi dot is equal to theta 1 dot minus theta 2 dot, right, which is equal to 2 pi 1 by T1 minus 1 by T2. where all these things are constant, right? So now I could use the uniform oscillator once again for this dynamical system. Okay, so in that case, what is the time period for this phi, which is 2 pi by this thing, right? So the time period, the capital T, which is equal to 2 pi of this thing, right, phi dot, right, which is equal to, so 1 by T1 minus 1 by T2, the whole inverse. Okay, so that's the time period. But if you see, so this is an example for uniform oscillator, but sometimes there could be a chance that P1 and P2 are known to each other. Okay, if they are known to each other, what will happen, they would like to run together. Okay, if they would like to run together, maybe the P1 will slow down, okay, a little, okay, and P2 will try to catch up the person P1, okay, and when he will slow down and when he will catch up, it depends on what is the gap between these two people, okay, which is phi. So there is a possibility that phi dot is not just constant, or let me write it here. So phi dot is not just constant, it could be a function of the gap, which is phi. Okay, at that time this oscillation will not be a uniform oscillation. Okay, so that is known as non-uniform oscillations. Okay, and in the next video we will discuss about non-uniform oscillators. Thank you.